All right, so that's objective 2, again, using tree diagrams to calculate conditional probabilities. Example 2, how reliable are mammograms? Many women choose to have an annual mammogram to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't, a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does, a false negative. So again, if you think about COVID-19 right now, a lot of this is going on, right? The validity of the tests, and all that fun stuff. Suppose that we know the following information about breast cancer mammograms in a particular population. 1% of women aged 40 or over in this population has breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. And for women who don't have breast cancer, the probability of a positive mammogram is 0.06. A randomly selected woman aged 40 or over from this population tests positive for breast cancer in a mammogram. Find the probability that she has breast cancer. Okay, I have this broken into 2 more slides. So on this slide, we're going to make the tree diagram. Okay, so again, we have a lot of information here, but let's talk about the stages. So your first stage is about having cancer or not. So either you have cancer, and breast cancer if you want to put, or you don't have cancer. And then the second stage is your test, right? And you either get a positive result or a negative result, a positive result or a negative result. So there's your stages, right? So now we got to fill in the numbers. It says 1% have breast cancer. This is 1%, which is 0.01, has breast cancer. That means 1 minus 0.01, which is 0.99 or 99%, does not have breast cancer. And now these two are conditional probabilities, right? For women who have breast cancer. So if I have breast cancer, the probability of a negative test, so negative test, is 0.03. So then we have to do 1 minus 0.03 to get 0.97 for this branch. Remember, they have to add to 1. And then this one for women who don't have breast cancer, so no cancer, the probability of a positive is 0.06. So they can do 1 minus 0.06 to get 0.94. And here is our tree diagram. So I'm going to copy and paste this onto the next slide, and we're going to take a look at the actual problem. Okay, so let's reread the question. So the question says, a randomly selected woman aged 40 over tests positive. So we know she tests positive. This is the given. She's testing positive. We want to find the probability that she has cancer. So let's let P be for positive and C be for cancer. We want to find the probability that someone has cancer given that she tested positive. Well, conditional probability formula says the given goes on the bottom. So on the bottom is going to be the probability that someone tested positive. And on the top, we're looking for the probability that someone tested positive, not R, P for positive, and had cancer. Okay, so let's do the bottom first, right? I always like to given. So what's the probability that someone is positive? Well, there's actually 2. There's these 2 pathways. So we have to determine the cancer and positive and the no cancer and positive, and that's going to be the bottom. So in my bottom, I'm going to do 0.01 times 0.97. That is the cancer and positive, plus I'm going to do the 0.99 times the 0.06. And that's those who had no cancer and tested positive. So there's all those who tested positive, right? And you gotta multiply along the pathways. And now the top is just those who tested positive and have cancer. Well, that's going to be this top route. Cancer and tested positive, right? So that's going to be 0.01 times 0.97. So there is our fraction. I'm going to put all that in at once. Let me take a picture of it. Here we go. Okay, let me get out of here. Let's go to Desmos Graphing Calculator. Let's clear that. So I'm looking at, so I'm going to put the fraction bar in first using the fraction key. Okay, so the top is 0.01 times 0.97. And the bottom is going to be 0.01 times 0.97 plus 0.99 times 0.06. And there we go. And I'll round to 2 decimals because it makes it look nicer. So what is the probability that someone has cancer given they tested positive? 0.14, and that would be roughly 14%. Right, so there we go, and that's how we use these. That's how we use these tree diagrams to do conditional probabilities. So the moral of the story is, right, when you have a test, you should make sure you get two people's opinions. They call that a second opinion, right? Because if I take a test and someone says I have cancer, I better make sure that I really do. So same thing with COVID. If I went to go take a test for COVID and it said it came back positive, I might go get another one because I'm not sure about how reliable these tests are right now. Okay, so that's just my opinion. I know it costs money, but it's your life versus money, right? Okay, so hopefully this helped and you do well on the homework. This is an important section. Let me know if you need any help.